Hello, this is Mr. P, and today we're going to learn about sequences and series. The book gives us our definition of a sequence, both an infinite sequence or a finite sequence. The infinite sequence is the one where the terms keep on going forever, and a finite sequence has a finite number of terms. And the individual values in the list of terms, those are called the terms. And we can represent a sequence using different notations and represent it in different ways. We can simply list the terms, such as you see here, or we can represent them as a set of numbers where the general term would be some formula for the nth term. So if I plug in a 5, for example, in for n, then that would give me the value of the fifth term in the sequence. And we're going to see as we go through our examples that it is possible to start your sequence with n equals 0 rather than n equals 1, but officially your sequence is going to be a function whose domain is the set of positive integers. So the first value in the sequence you get by having 1 as your input, the second value or term you have 2 as your input, etc. But this can be shifted to using 0 rather than 1 in certain circumstances. But most of this is going to be more evident in examples. So let's look at an example where they want us to write the first 5 terms of the sequence given by this formula for the general term. A sub n being this formula means that is a general term. So to find the first 5 terms, I simply use n equals 1, n equals 2, all the way up through n equals 5. So the first one, then this is our algebraic approach. We're going to substitute 1 for n, so it's going to be negative 1 to the first power over 2 times 1 minus 1. When we clean that up, we get negative 1, and that is our first term. Since n equals 1, that's our nth term, is our first term. And next we substitute n equals 2 in the same manner, clean it up a little algebraically, and we get 1/3 being our second term. Of course, for a equals 3, for n equals 3, you have a sub 3 is going to be negative 1/5. That is our third term. Substitute n equals 4, and again, we're substituting into this same equation here, into the same general form. We get that the fourth term is 1/7. And finally, our fifth term, a sub 5, we end up getting negative 1/9. And you can double check the arithmetic here yourselves, but it is accurate. So those are our first five terms which they wanted us to list. One thing I do want to point out here, and this is something that's good to notice right away, is notice how my first term is negative, second one's positive, third one's negative, then positive, then negative. If you get an alternating signs in your terms, then usually in your general term you're going to have negative 1 to some power. So notice how whenever n is even, you're going to get the numerator will be even. Whenever n is odd number, you will get an odd, you'll get a negative numerator. So that's why our signs keep switching in this particular sequence. All right, let's look at another example, another way to write it. Notice how this time they're using the set notation. So the set of b sub n is going to be the sequence defined by this general term. So they want us to write down the first 6 terms. So we're going to start with n equals 1 and go up through n equals 6. So starting with n equals 1, we have 1 minus 1 would be 0. And negative 1 to the 0 is positive 1. And then 2 over 1 would be 2. So 1 times 2 would be 2. And we can see that b sub 1 is indeed the value 2. And we can continue doing this, plugging in 2 for n, then 3 for n, and we're going to get all of these values down here. You can double check the values yourselves. And that would be listing the terms, listing the first 6 terms. Now they also ask us to graph it by hand. Now the graph of a sequence is not going to be a line or a curve like you're used to. It's going to be a set of points. because these are discrete numbers. We're inputting integers, and then we're getting out a value. So n is actually our input in this function, and the output is whatever b of n is. So here, if n is 1, then b of n is 2. If n is 2, then b of n is negative 1. That's our input-output. So when we plot those points, it's going to look like this. Notice how 1, 2, that's the first point here. And then 2, negative 1 would be 2, negative 1 would be that point. Our next one would be 3, 2/3. So 3, 2/3 is that point, etc. So the graph is actually going to be 6 different points on the plane. Now we can also do this on the calculator, and I want to walk you through the calculator process because it's a little different than everything we've done before. So we're going to go ahead and turn on our calculator, and we're going to use the TI-84 Plus for this. And we're first going to see how to get this list on the home screen using the correct functions, and then we're going to see how to get this graph. So starting with this list, I'm going to first of all go to mode, and the mode I want to make sure I'm in sequential mode, SEQ. This will be the first time we're using sequential mode. And then looking ahead, in order to get the dots correctly, I do want to be in dot mode rather than connected mode. So I'm in sequential mode and I'm in dot mode. Okay, when we go to our home screen, so I'm going to do second quit to get to the home screen. I want to make a list of these terms as I go from n being 1 to n being 6. So here I'm going to go to second stat is the list, is what I want to go to. And I want to go 1 to the right so that I get to operations. So second stat is list, and then I want the operations menu, and I'm selecting number 5 here, which is the sequence function. So if I hit 5, that gives me sequence. Now the syntax for the command is I want the sequence of the general term, and this would be our general term. So I'm going to open parenthesis, -1, make sure it's negative, not minus. Close parenthesis, to the, and now I'm going to open parenthesis again because I have more than one term for my exponent. So it's n minus 1. Now notice n is that same variable button. If you're in function mode, when you press that, you get x. In parametric mode, you press that, you get t. In polar mode, you press it, you get theta. And in sequential mode, you press that, you get n. So it's n minus 1, close parentheses. So it's -1 to the n minus 1. And then I'm going to multiply that by 2. If I want to open parenthesis again, 2 divided by n, close parenthesis. That way I know I have it exactly the way it is here. So the syntax, again, for this command is the sequence of the general term, which we just put in the general term, and then comma, and the comma is the button right above the 7, and it's comma, the variable that's being indexed, and the variable that's changing with each iteration is n, so it's comma n, and then comma from the lower bound, or the lower limit, which is 1, because we're going from 1 to 6. So it's comma 1, comma 6. So again, it's the sequence of the general term as n goes from 1 to 6. And then I can close my parenthesis. Now there is an additional optional parameter we could put in there. We could put a step in there if I wanted to go by 2s or go by 3, count by 2s or 3s, I can do that. But if you don't put anything in there, it just assumes that you're counting by 1s. So once I have my command in there, I hit enter, and it gives me the set. Notice the braces here, and it gives me the set of numbers. However, it gives it to you in decimal form. So the easy way to clean that up is once you have that, you go to math. You want the answer to go to a fraction, so you're going to select number 1. Notice how answer to fraction, when you hit enter for that command, and now it gives you the set in fractional form. And notice how the set continues off to the right of the screen. All you have to do is hit the right arrow to scroll either right or left so you can see all your numbers. So notice how it ends with -1/2, and then 2/5, and then -1/3. So that gives us all of these numbers. And the way to now graph these is we can go into y equals. Again, we're in, make sure our mode is sequential mode and in dot. So if we go to y equals, our n minimum is going to be 1. We're starting with n equal 1 and ending with n equals 6. And u of n is the general term. So putting in the general term again, it's going to be open parenthesis, -1, close parenthesis, to the n minus 1, close parenthesis, and then times 2 divided by n. So I put my general term in there for u of n. That's the function that gives me my term depending on what n is. N is the input, and the value of u sub n would be the output. So I do that, and then I'm going to go to Window, and we said earlier that we're starting with 1 as our n min, and our max we're going to 6. I'm going from 1 to 6. So from 1 to 6, I'm going to start at 1. I'm doing 1 for the step, so that's all good. And then x min, x max, in other words, the window, I'm going to let it set it automatically. So I'm going to go to Window. This is going to be a finite graph. So I'm going to go to Window. I'm going to go to Zoom. And then I'm going to choose Zoom Fit, which is Zoom 0. But I will show you on here. Zoom Fit is Zoom 0. So you can arrow down and hit Enter, or you can just hit the number 0 when you're on that list. And here is our points being plotted. Now, it fits the window to just barely fit the points, so the scales are different. If you wanted to square up the window, you could. But from here, if you want to find out what exactly are these values, then once again, you can hit Trace. And when you go to Trace, it'll jump to the first number, which you see the cursor blinking up here. In other words, it'll go to b sub 1 in this case. So notice when n equals 1, x is 1 and y is 2. So 1, 2, that corresponds to that point. And then if I hit the right arrow, it goes to the point when n equals 2. When n equals 2, we have 2 comma -1. When n equals 3, we have 3 comma what amounts to 2/3, and etc. You can keep going through your points. Going right goes to the next higher value of n. Going to the left goes back to the lower value of n. Okay, now just as a quick recap, because these will be in the notes, for the procedure for the calculator solution where you just make the list is, first of all, we want to make sure our mode is in sequence and dot. Then we're going to go to the list menu, which is second stat. We're going to arrow to the right, so we're at operations. And we're going to select number 5, which is sequence. And the syntax for the sequence is our general term, then the variable you're indexing, then the lower limit, then the upper limit. So once you put those in and hit enter, you'll get a bunch of decimals. But then if you go to math and answer to fraction, it's going to change them to fractions. And if you want to see numbers to the right, in other words, after the first 3 terms here, if you can arrow to the right or to the left to scroll along the set and see all of the numbers. Alright, and then the calculator way to plot them or make the graph was, again, we must be in sequential and dot mode. We're going to go into y equals to enter your general term. You're going to put that in u of n. You're going to put the general term. And then in the window, we're going to make our min max, and n min and n max is going to be our lower and upper bounds from 1 to 6. Then we're just going to do zoom fit, which fits a window to all of our numbers. And then, of course, we can use trace and arrow around to be able to see what the numbers are. Alright, so moving on to another example, let's look at finding the nth term of a sequence. Here, and this can be usually one of the toughest things to do, is try to figure out what the general term, what that nth term of sequence is. This is where you build that pattern recognition skill. So here we have A is simply the list or the sequence 1, 3, 5, 7, etc. It's the odd numbers. And B looks a little tougher. It's 2, 5, 10, 17, etc. That pattern will continue indefinitely. So with part A, we want to try to compare these numbers, which would be the output, to the inputs, which would be the integers 1, 2, 3, 4, 5, etc. So if we compare the n's 1, 2, 3, 4 to the terms themselves 1, 3, 5, 7, sometimes matching them up term for term helps you find that apparent pattern a little better. Now, hopefully you know already that in the general term for an odd number can be written as 2n plus 1 or 2n minus 1. And in this case, the 2n minus 1 is the one that works, because if n is 1, then 2 times n plus 1 would be 3, and 2 times n minus 1 would be 1. So the apparent pattern here is if we double the n and then subtract 1, you will get the correct term. So for example, 4, if we double it, we get 8, and that's 1 more than the number we wanted. 3, we double it, we get 6, that's 1 more. 2, we double it, we get 4, that's 1 more than what we wanted. So the apparent pattern is 2n minus 1. That would be our general term. For the second one, a little more deceptive. If we match up the n's with the terms themselves, then it's not just a matter of doubling, because you double, you get the first one. If you double the second one, you don't get the second one. So it's not just doubling. There has to be something else going on here. So you want to try the common operations, which is, of course, multiplication, division, addition, subtraction, squaring, square roots. And one of the things we should hopefully notice, if we square 1, 2, 3, and 4, we're going to get 1, 4, 9, and 16. Comparing those to these values, 1 is 1 less than 2, 4 is 1 less than 5, 9 is 1 less than 10, and 16 is 1 less than 17. So the apparent pattern here is n squared plus 1. Square the n, add 1, and then you get your term. Like I said, it takes a little bit of practice and a little bit of trial and error to try to figure out these apparent patterns. But the more you do them, the more you'll recognize certain patterns. Alright, so let's look at a couple more here. We're going to give you a chance to do some of these, so if you want to pause the tape, you can do that and try to figure these out yourselves. But when you do come back, you should hopefully recognize on the first one that you can write e as e over 1, and that way it makes it easier to compare. So you'll notice in the numerator you have e squared, e cubed, e to the fourth. So in general, you're going to have e to the n. So in the first term, it's e to the 1 when n is 1, when n is 2, when n is 3, etc. So in the numerator, we're going to have e to the n. And in the denominator, you have 1, 2, 3, 4, which is just n itself. So hopefully the first one was easy enough for you, where a sub n, the general term, is going to be e to the n divided by n. And on the second one, again, it would be helpful to recognize that this is 1 over 1 for the first term. So the top, or the numerator, stays constant. So that it will be constant then in your general term. And notice in the denominator you have 1, 3, 9, 27, which is just multiples of 3. So it looks like we're multiplying by 3 every time. So we can think of 27, for example, as 3 cubed. 9 would be 3 squared. 3 would be 3 to the first. And even the number 1 is 3 to the 0. So if we think of it that way, then hopefully you can figure out that our pattern is going to be 1 over 3 to the n minus 1. Because that way, if n is 1, then 1 minus 1 is 0, 3 to the 0 is 1, and then if n is 2, 2 minus 1 is 1, 3 to the first is 3, so we're getting the correct denominators. 1, 3, 5, 7, etc. We already saw that one actually. It's either going to be 2n plus 1 or 2n minus 1. If you start with n equals 0, it'll be 2n plus 1. If you start with n equals 1, which we're doing here, then it will be 2n minus 1. For D, hopefully you recognize 1, 4, 9, 16, 25. Hopefully you recognize those as perfect squares. So this is 1 squared, this is 2 squared, this is 3 squared, 4 squared, 5 squared, etc. So our pattern there is simply D sub n is going to be n squared. And the last one can be a little tricky. Again, we're going to think of the first term as 1 over 1. And then the numerator is just 1, 1, 1, 1, always ones. The denominator is 1, 2, 3, 4, 5, etc. So it's 1 over n. But notice how we have a positive, then a negative, then a positive, then a negative. And we saw that before. That happens when we take negative 1 and raise it to a power. And we just want to be careful that we get the first term right, because we're either going to raise it to n plus 1, or n minus 1. We have a little bit of freedom there. Well, if n equals 1, if I raise negative 1 to the first power, that would make the first term negative, so that's not what I want. So therefore, I want to use either n plus 1 or n minus 1. Either one would actually work. But if I raise negative 1 to the n plus 1, that means if n is 1, then I'm raising negative 1 to the second power, which makes it positive, so the first term's positive. And then it will alternate from there on, positive, negative, etc. And this is all being multiplied, of course, times 1 over n. So you get 1 over 1, 1 over 2, 1 over 3, etc. Alright, so it just takes a little bit of experience with those, and you'll start to get those a lot quicker. Alright, let's look at factorials. Before we get to factorials, let's look at the Fibonacci sequence. All of these sequences, anytime you can write a sequence as a general term, you can also write it as a recursive sequence. The general form, or using the general term, says that you can jump to a sub 18, for example, by just plugging 18 into the formula, into that general term. A recursive sequence defines your sequence a little differently. It defines your sequence based on the previous term, or in this case, the previous couple of terms. The Fibonacci sequence, which is one of the most famous sequences, we're going to talk a lot about it later, actually. It starts out with a sub 0 being 1, a sub 1 being 1, and these are called the seeds. And then from there, the recursive rule, says to get any term, you simply add the two previous terms. So if a sub k is the term you want, then k minus 1 is the term just before it, and k minus 2 is the term just before that one. So to get a term, you simply add the two previous terms. So if a sub 0 is 1 and a sub 1 is 1, then the next term, a sub 2, I get by adding these two terms. 1 plus 1 gives me 2. To get the third term, I'm going to add the 2 plus the 1 to get the 3. And then 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. 13 plus 8 is 21, etc., etc. That's called the Fibonacci sequence, and we'll see a lot of applications of this down the road. Now going back to the factorial, this is something you're going to see a lot, this notation, and with an exclamation point. It doesn't mean you shout it when you say it. It means n factorial is defined as 1 times 2 times 3 times 4 all the way up to whatever the number is. It's the product of all those numbers up to that number. And then as a special case, it defines a 0 factorial as 1. This is how most books define factorial. However, there is an alternative definition that I sort of prefer because it gives more meaning to 0 factorial. The alternative definition, which I've given you, is that n factorial is also equivalent to the number of distinct ways that the objects in a set of n objects can be arranged. For example, let's say you have 3 distinct objects in a set. And how many ways can you arrange them? Well, in the first position, you have 3 choices for your first position. And then in your second position, you only have 2 choices because you made a choice in the first one, so there are 2 remaining objects to place in that second position. And then in that third position, whichever one you didn't use has to be there. So the total number of ways you can arrange it would be 3 times 2 times 1, or in other words, 3 factorial. When you think of it this way, then 0 factorial actually does make sense because a set of 0 objects is the empty set. And how many ways can the empty set be arranged? Well, it can only be arranged one way. The empty set is the empty set. Alright, so let's look at an example here where this sequence has factorials in it. And they want us again to write the first 5 terms of the sequence. So again, we're going to start with brute force method here. We're going to start with n equals 1, substitute in the n, so you have 2. I'm sorry, actually they wanted us to begin with n equals 0. They told us in the directions. So starting with n equals 0, that means to get 5 terms, we're going to end with n equals 4. So we start out by substituting in the 0, and that gives us 1 as the 0th term. Remember, the nth term, if n is 0, means that that is the 0th term. And then if n is 1, we do the substitution, and we get 2 as the first term. And likewise, we're going to substitute in the value of 2 for n, and then we're going to substitute in 3 for n, and then 4 for n, and then we're going to stop because that is 5 terms. Remember, from 0 to 4 is 5 terms, just like from 1 to 5 would be 5 terms. And we're done with that one. Now, when simplifying, a lot of times you're going to have factorials in the numerator, factorials in the denominator, and you want to be able to simplify these expressions. So starting with the first one, the long way to do it, of course, is just to rewrite the numbers as the products that they are. For example, here, 8 factorial is 1 times 2 times 3 times 4, etc., all the way up to 8. 2 factorial is 1 times 2, 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. And then you cancel out whatever you cancel out. 1 through 6 cancels out with 1 through 6. And then the 2 goes into the 8 4 times. So 7 times 4 would be 28. So that would be one way to do it. An alternative way to do it, which I do prefer, is to recognize that 8 factorial, you can break that up as 8 times 7 times 6 factorial. And when we recognize that, 8, in other words, 8 factorial is 8 times 7 times 6 factorial, then we just cancel out the 2 factorials. And again, 2 factorial is 2 times 1, so 2 goes into 8 4 times. 4 times 7 is 28. So I think the alternative solution can be a good time saver when you have that opportunity to use it. Alright, looking at the second one here, the book, of course, did it the long way. And when you do all the cancellations, you get 2. But you can think of 3 factorial as 3 times 2 factorial. So those cancel out, leaving just the 3 in the denominator. And 6 factorial is 6 times 5 factorial, which cancels those out. So you have a 6 in the numerator, 3 in the denominator, which is what we have here. 6 divided by 3 is 2. And it even works with the variables as well. N factorial is 1 through n. Remember, the 1 just before n is n minus 1. And then n minus 1 factorial is 1 through n minus 1. Notice how those two can cancel, and all that's left is the n. Or in other words, n factorial is n times n minus 1 factorial. And then the n minus 1s would cancel. Alright, so now that we have the factorials and we have our sequences, we're next going to look at summation notation. When we add the terms in a sequence, that's called a series. And here, the notation we use for these is the capital sigma. It's the Greek letter sigma. And the way we lay it out is on the bottom we have our indexing variable. I is the index of the summation. And then we're going to go from the number 1 here is the lower limit, or in other words, the lower limit of summation, sometimes referred to as the lower bound. And then the number up top here is the upper bound. So the big E here, the big summation, means we're taking the sum as I goes from 1 to n. And that's how we read this. It's the sum of whatever this expression is, which will have an I in there somewhere usually. We're taking the sum of this expression as I goes from 1 to n. So that'll be a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n, going from 1 to n. So if we look at the first one here, we have the sum as I goes from 1 to 5 of 3i. Well, that means we're going to plug in 1 for I, then we're going to plug in 2 for I, then 3 for I, each time getting a term, and then we add all those terms. So here it's 3 times 1, plus 3 times 2, plus 3 times 3, plus 3 times 4, plus 3 times 5. And notice here that there is a neat little algebraic thing we can do here to save some time. Since each term has 3 in it, we can factor that 3 out, and then this 3 times 1 plus 2 plus 3 plus 4 plus 5. Add those together, you get 15. 3 times 15 is 45. So the sum, as I goes from 1 to 5 of 3i, is 45. And this factoring the 3 out, I want you to keep that in mind, because one of the properties we're going to see later is I could have, if I wanted to, factor the 3 out to begin with. We're going to see a property where if you have a constant times your expression, you can factor that out of the summation altogether. That's how every term is being multiplied by 3, so we could have multiplied by 3 at the end, just like we did. Alright, for the second one, we're going the sum SK goes from 3 to 6. You don't always have to start at 0 or 1. So notice how the first thing we do is substitute in 3. So it's 1 plus 3 squared, then 1 plus 4 squared, 1 plus 5 squared, 6 squared, etc. So that's 9 plus 1 is 10, 16 plus 1 is 17, 25 plus 1 is 26, etc. Add them all together, you get 90. Even symbolically, we can do this. We want the sum as n equals 0 to 8. So this time we're starting with 0. So here we're going to have 1 over 0 factorial, which is not 0. Remember, 0 factorial is 1. And then I'll bring this down just to here. Actually, let me do this. There we go. Let me do this. Alright, so 1 over 0 factorial, 1 over 1 factorial, etc. Is going to give us these numbers. Notice how the factorials get pretty large pretty quickly. If we add up all these numbers, we get approximately 2.71828. And something you're going to see in calculus is when this expression goes from 0 to infinity, as the limit of that sum is going to be the number e. E being the 2.71828, etc., etc. Alright, now also one other thing to be aware of is notice how two different sums can actually give you the same value and look different depending on whether they're starting with a 0 or starting with a 1. So the sum as I goes from 1 to 3 of this expression is the same as the sum as I goes from 0 to 2. Notice from 1 to 3 there are 3 terms, from 0 to 2 there are 3 terms. And here, if you start with 0, then 0 plus 1 is 1. Here, if you start with 1, then I is just 1. So they have the same first term, and they're going to have the same number of terms, and each term is going to be the same. So just be aware that you can, when you're writing the summation yourself, you can write it in more than one way. Alright, next we're going to look at evaluating or expanding some of these sums. First, we're just going to write them out. We're just going to expand them out. We're not going to actually find the value of the sum. So here, this is the sum as k goes from 1 to 10 of 1 over k, and that's simply going to be, we start with 1, so we substitute in 1, so 1 over 1 is 1. Then we substitute in 2 to get 1 half, substitute in 3 to get 1/3, etc., up into 1 over 10. And if we added them all together, that number would be the value of the sum. For this one, we're going to do it symbolically. It's k is going from 1 to n. So again, we're going to start out with 1 is going to be 1 factorial. And then we plug in 2 to get 2 factorial, and 3 factorial, 4 factorial, etc., all the way up until n, whatever the number n is. So this is a way to express that finite sequence. Or actually finite series, because it is addition. Alright, let's look at one other thing. We want to express each sum using summation notation, so this time we're going in the reverse order. We're given the series, and we want to try to write it as a summation. So here, I first want to look at, this is the same as recognizing the pattern from before. I'm going 1, 2, 3, etc., all the way up to 9. So my lower limit is going to be 1, my upper limit is going to be 9. And each time what I'm doing to the number is I'm squaring it. So if we use k for our indexing variable, then we can say here that we're going from k equals 1 to k equals 9. And each term will be in the form of k squared. So therefore, my answer will be the sum as k goes from 1 to 9 of k squared. And for the second one, notice how they actually show us what the general term is going to be. So the pattern starts with this being 1 over 1. So in order to have a 1 in the denominator, we would need this to be 2 to the 0, which would mean n would have to equal 1. So our lower limit is going to be 1, which means we can use this as our general term, and our upper limit would be n. So for this one, we're going to go from k equals 1 to k equals n, again k being our indexing variable. So this is going to be the sum as k equals 1 to n of that general term, and notice how I'm using the k because that's what we're actually substituting in. I'm not using the n, I'm using the k because that's our index of summation. Alright, let's look at some properties for sums. And the first one I mentioned before, if we have, or actually the second one is the one I mentioned. The first one is if you have the sum as your index goes from 1 to some number of just a constant, that means that I is not involved in the general term at all, then your each successive term is going to be the same. So the number of them that you're adding up would be whatever 1 to n is. So you're going to have n terms, and each of them are going to be c, so c plus c plus c plus c n times would be the same as c times n. So that is a little shortcut formula. If you're taking the summation of a constant as your expression, then it's simply going to be the number of terms times that constant. The second one is the one I was talking about. If you have a constant times some expression, it is possible to factor that expression or factor that constant out of the summation. And this can make your calculations a lot simpler. Rather than having to every term multiply by that number to get large numbers they're adding together, you can add a bunch of small numbers together and multiply it by the c at the end. Notice here how the sum of a sum is the same as the sum of the individual sums. So I can sort of think of this as distribution. If I have this expression plus this expression, then I can take the sum of the first one, the sum of the second one, and add them together. This works very well when you're doing the sum of a polynomial, because then you can break it up into term by term. And it works for addition just as well as it works for subtraction. Now, we mentioned before the word series. The series is what we get when we add up these terms in a sequence. So a series is usually an infinite series is what we talk about in mathematics. An infinite series means that we're going to add up all of the numbers through infinity. There's going to be an infinite number of terms. And in order for this to have a sum, we're going to have the terms get smaller and smaller as we go along. Otherwise, it's not going to have a sum. It will blow up to infinity itself. So it is possible in mathematics to add an infinite number of terms and get a finite number as long as your terms are converging, what we say converging, to a limit. So here you can add up the partial sums if you have a finite series. If you're talking about the first n terms of a sequence, then we can add up those first n terms. That would be a finite series. Or if you add up all the terms, that would be an infinite series. And we're going to see in a little later sections some shortcut formulas to calculate both of these. But first of all, let's just look at the intuitive approach. So let's look at finding the sum of this series. This series is the sum as I goes from 1 to infinity of 3 over 10 to the I. And I want us to find first the third partial sum and also the sum itself of all of the terms. So starting with the partial sum, we're only looking for the first three terms. So we start with I being 1, and that's 3 over 10 to the first. If I is 2, 3 over 10 squared, 3 over 10 to the cubed, etc. And dividing by a power of 10 is just moving the decimal point. So here we get 0.3 plus 0.03 plus 0.003 gives us 0.333. That would be the third partial sum of this series, the sum of the first three terms. Now, if we wanted to find the sum itself, we would continue this process infinitely. And luckily it does form a pattern that we can recognize. So notice how 0.3 plus 0.03 plus 0.003 plus 0.0003, etc. means each term is putting a 3 in the next digit of the decimal expansion. So it ends up being 0.3333 repeating, which is exactly equal to 1/3. So once again, notice how this is a sum of an infinite number of terms. The terms are getting smaller as we go along, and it is possible for it to sum up to a finite number like it does here. So the sum as I goes from 1 to infinity of 3 over 10 to the I is exactly equal to 1/3. And we're done.